Good afternoon, everyone. My name's Jennifer Harding, and today I'm going to present about the practical applications of quantum computers. So we'll be going over what a quantum computer is, a very high-level overview of different types of quantum computers, as well as investigating some of the interesting use cases that are out there for us today. So to start, a little bit about me is I'm currently a senior solutions architect at Capco. But I really have a strong passion for quantum computing and the use cases and potential impact that we're going to see over the next few years. I have a background in studying physics at university, but I also worked as a quantum ambassador and Qiskit advocate at IBM, as well as a quantum computing startup that was looking at creating quantum computers using Diamond, where I worked as a quantum application developer specializing in quantum chemistry. So throughout this presentation, I'll go over, how Diamond quantum computers work at a very high level, as well as also discussing why I think the use cases in quantum chemistry are particularly interesting. So this is just re-summarizing a lot of what I've already said about, we're going to have an introduction, the basics of qubits, different types of quantum computers, and where we are today, as well as looking at use cases. Okay, so introduction to quantum. I understand that lots of people will be coming here today with different backgrounds and different experiences of quantum. So some people may be very experienced and already know the basics of quantum mechanics, but I will start off with what makes a quantum computer. Now, what a quantum computer is, physically is it can be very different implementations of things. But what we have is kind of a few key fundamental concepts which all quantum computers exhibit. Now, the first one is the idea of superposition. So classical computers like the laptops and computers and data processing centers that we use today are all based on bits, and bits can either be in a state of either 0 or 1. But one of the fundamental interesting parts of qubits, which are what quantum computers are based on, is it can be either 0 or 1 or any state in between 0 and 1. Now, what we do to represent this kind of all of these possibilities in between 0 and 1 that a qubit state is able to be in is we have this thing called the block sphere. And we say that the state of the qubit can be at any state in the block sphere at any given time. So, it could be exactly 0 or it could be exactly 1, just like a classical computer is, but it could also be a little bit of 0 and a little bit of 1, and it can kind of take any state along around this sphere. And people look at this and they're like, wow, we have an infinite number of possibilities of the state of a single qubit compared to only the 2 states that we have for classical bits. But actually, unfortunately, as soon as we measure qubits, it collapses into a state of either 0 or 1. So when we're measuring it, the measurements that we get will always be either 0 and 1. And what we do is we take measurements lots and lots of times in order to find out more information about where the qubit is. So for a very simple quantum algorithm, it's the case we'd actually perform over 1,000 measurements in order to tell us more information about the qubit state. So it's not like a classical computer where it's kind of set, it's very set in what it is. With quantum, there's always an additional element there, and we need to take multiple measurements in order to find out more information there. But what the real key interesting part of a quantum computer is the idea of entanglement. So this is the idea that the states of the qubits are kind of joined together, and the state of one qubit is able to tell us information about the state of another qubit. So what we have here is, we could have qubit 1 and qubit 2. And when we measure, say, qubit 1, would be able to find information about what the state of qubit 2 is. So we do that by creating some kind of connection between the two qubits. And I will talk a little bit about how we create that connection later on during the call. But it's the idea of saying, well, if qubit 2 is in the state of 1, then, is in the state of 1, then qubit 1 will also be in the state of 1. So it is this idea that everything is linked together, which is what is very, very powerful about a quantum computer. And what that is able to do is it's able to expand the number of computational states which are available to us. So when we have one classical bit, that can be either 0 or 1. It says here there are 2 states, but it's really only 1. Whereas when we have 1 qubit, again, we're not really seeing much power there. But when we have 2 qubits, then we have 4 computational states available to us. And when we have 3 qubits, then we have 8 computational states. And the number of states that we have available to us exponentially increases with the number of qubits. So it's the case that we're able to see a strong advantage over classical computers, actually with only a small number of qubits. So people may think, we need like hundreds or thousands of qubits, but we can see advantage over classical computers with a smaller number of qubits. But there are many challenges which we'll discuss later in this call that come along the way that means that this isn't quite as easy as it looks on paper. Whilst we would love to have perfect and unentangled qubits, that's not always the case. And there are many challenges that face the journey towards quantum computing that we'll be looking at during this call. So now I'm going to go a little bit into the different types of quantum computers, because whilst these ideas of entanglement and superposition sound super interesting, it can sometimes be a little bit confusing on what that means physically and how these are created. Okay, so these are some of the popular types of quantum computers that we look at today. So you can see that these are based on lots of different types of technology and lots of different types of materials. One thing that's quite interesting about quantum computers that's often overlooked is the idea that quantum technology is something that we already have today. There are plenty of use cases of quantum technologies, and there are plenty of use cases of things that use superposition, or just some of the weird and wonderful properties of quantum mechanics. And quantum computing is just an extension of these. And the even more important thing to remember is that everything around us at a very small scale is quantum. Atoms, molecules, kind of very, very small things all exhibit quantum behavior. So what we're doing with quantum mechanics or quantum computing is we're exploiting these weird and wonderful properties that we have. We're exploiting these properties that are kind of fundamental to nature to create this type of computer. It might sound really strange to some of us, it still sounds quite strange to me, but this is fundamentally quite a natural thing. So I'll be going into a little bit more detail on how these are actually created. So we have superconducting and ion-trapped qubits are some of the most popular quantum computers that we have out there. Lots of the stories in the news of what we hear today about quantum computers tend to be referring to ion-trapped quantum computers. Superconducting quantum computers. But now I'll go on to talk a little bit about what a quantum computer could be. So first of all, I'll start with a diamond-based qubit. And similarly to what I discussed earlier, a diamond-based qubit is actually used for practical applications today. So kind of it's a very, it has lots of practical use cases today for sensing and for finding out properties of, say, a large diamond. So I think that's one really important thing that we have to consider, that qubits and quantum technology is used, but we'd like to find a way that it can be used on a larger scale. So for a diamond-based quantum computer, obviously for a diamond, we have a carbon lattice. And what we do is we shoot a nitrogen laser on the lattice, and it displaces a couple of the carbon atoms and it replaces it with a nitrogen atom. But there's also a little bit of a hole left. There's also a little bit of a hole left when the second carbon atom is displaced. And what that's able to do is it kind of provides an imperfection within the material. And this can actually just be found using specialist microscopes. So we have this nitrogen vacancy center. And one thing that's quite interesting about a nitrogen vacancy center is for the qubit itself. So these energy, so for the state of 0 and 1, this actually just represents different energy levels of the electron spin. And why this is interesting is we prepare the qubit by shining another laser on it, which excites the nitrogen, which excites this NV center. And when it's excited and when it relaxes, there's actually a photon that's emitted. So some light is emitted, and you can actually see what state the qubit is in from the light that's emitted. So we can tell whether it was in the state of 0 or 1, even just by an optical observation. So again, just a further reiteration of the fact that not all of these concepts are as weird as we may think they are. What's quite interesting about a diamond-based qubit is because diamonds, as we know, are kind of very strong materials. They're very, what diamond-based qubits have is they're able to stay in an interesting state for longer than lots of other types of qubits, and they're able to work at room temperature, which many other different types of quantum computers are not able to. The unfortunate thing about diamond-based quantum computers is there's a big challenge in being able to tie lots of different qubits together. It tends to be the case that actually we only have, at the moment, we tend to just have 2 qubits maximum, and anything greater than that has not been published yet, but it will be exciting to see something in the future. So diamond-based qubit, it's very strong. There's a visible emission, and we have long coherence times. So it's definitely an interesting type of qubit, especially when we consider the use cases today. Now, a slightly more popular type of quantum computer, which we see a lot of in the news. So IBM and Google both have a superconducting quantum computer. And you may have seen images like the one on the left. This is what a lot of people tend to associate when they think of a quantum computer. But actually, what most of these kind of wires and brass elements are, is it's actually the fridge. It's actually what we're using to keep the quantum computer cold. Most of these wires are not actually well, okay, a lot are used for readout, but the microwave pulses that we apply, but actually the size of the quantum computer is mainly to keep the qubit and the circuits cold. So we kind of have these huge pieces of tech or these kind of huge pieces of machinery, which are used to keep the qubits at less than 1 Kelvin, so extremely, extremely cold. But what we have in the center is actually like a silicon germanium chip, as we can see on the right-hand side. So these 4 squares in the center are actually the qubits themselves. And as you can see, that's a very, very different manifestation of a qubit compared to the diamond qubit that we saw on the last slide. What's really great about this type of quantum computer, and the fact that a lot of the machinery is just for keeping the circuit cold, is the fact that upgrades only mean that you have to replace the chip inside rather than the whole cooling unit. So there will be additional wires which are required for the input and the read out measurements, but ultimately it's maybe not as big of a task as you'd expect it to be. But as the circuits themselves get bigger, the fridges will still get bigger too. The reason that the wires kind of look a bit messy and curly is just because there'll be thermal expansion and contraction to kind of go between the super cold as well as the room temperature. So that just allows a little bit of leeway to make sure the wires don't snap. And to go back to the circuit on the right-hand side, we can see the 4 qubits in the center. And if you look, you can see the wires. There are little connections between the qubits. So this is kind of created during the fabrication of the chip itself. And that is actually what creates the entanglement. So whilst on the diamonds, we have the coupling between the NV centers, here we actually have a physical connection which enables the entanglement. And to create the states that we want, we apply microwave frequency pulses to the circuit itself. So you can see these are kind of, I guess, 2 extremes of what quantum computers could look like. But I think it's an interesting idea, or it's interesting to think about, the breadth of different technologies that could be available to us. And just because we hear about setbacks or progressions that have happened in one field of quantum computing, that doesn't necessarily mean that it's always applicable to all of them. And when we're creating algorithms for quantum computers, so when we really want to think about, how do we make the best use of the entanglement, we also need to consider, well, which qubits can be entangled together, because not all of them have an all-to-all connectivity. It's often the case that one qubit is entangled to another, and then that qubit is entangled to another, and you kind of get this like longer chain rather than all qubits being able to connect. So we need to consider the topography of the quantum computer and the qubit technology in order to create the best circuits for us. So there are 2 different types of quantum computers. What makes a good quantum computer? So as I just mentioned, we're really looking at the connectivity of the qubits. We want to think about how much time the qubit stays in the state that we want it to be in, because for many different types of quantum computers, we're looking at like nanoseconds, microseconds, milliseconds. It's not normally the case that we've got a long amount of time that we can manipulate the qubits for or take the measurements for. All of these things need to be taken into account when you're creating the algorithm. So we need to think about the coherence time, but also how long it takes in order to actually measure the qubit itself, because you don't want to have a quantum computer where it takes a very long time to measure the state of the qubit, but the qubit has very quickly got out of the interested state anyway. We also want to look at how consistently we can get the qubit into the interested state, how reliable the qubit is, and things like that. So one of the other interesting things about an NV center is when we're putting the laser on it in order to get the qubit into the state we want, that can actually cause the NV center to ionize, and then it's no longer in a state that we're interested in, which is quite unfortunate. So there are loads and loads of different elements that we're looking at for what would make a good quantum computer, but that would probably take a whole hour presentation itself to go through them all, but this is just a high level. One of the other interesting things that has come up in recent years is the idea that actually the size, maintenance, and practicality of use should be taken into account. So for many different types of quantum algorithms that would run on a quantum computer, it could be the case, if we're having to take 10,000 measurements, well, do you take that all on one quantum computer? Do you split it across different circuits? How do you do that? Because if you need to run the same algorithm 10,000 times, that obviously takes quite a long time. And you need to think about, well, is it efficient to have, say, one quantum computer? Do I need two? Do I need three? If they're kind of a big 4-meter square type box, then that's not very practical to have multiple. So actually, you might say, even though a smaller quantum computer doesn't have as many qubits, it's much smaller, so it's actually kind of better for our data center or something like that. So lots of different considerations to take into place. As with any type of computing, as with any type of cloud algorithm or cloud application, it's the case, it just depends on what your use case is. So where is quantum today? We've had 3 separate claims of quantum supremacy, which you may have heard in the news around 2019. Was Google's announcement to say that they have managed to run something better on a quantum machine than a classical machine. But recently we've not heard any updates on this claim, or we've not heard anything additional to say that they've seen kind of the same type of advantage across lots of algorithms. Now, what a lot of people are saying about this claim is the fact, even though it outperformed a classical version of an algorithm, it's the case that it wasn't necessarily a useful algorithm. So all 3 claims of quantum supremacy, I think we can all agree it was able to do something better than a classical machine, but it's not something that's necessarily useful. I guess it's more of an amazing academic achievement, but not it's not necessarily an indication that would be able to see advancements in other areas anytime soon. And I think why this is also important to think about is the fact that just because we see a benefit or a speed up for one use case or one algorithm, it doesn't mean that we're able to see the same benefits for all of them. Now, there's also a metric called quantum volume, which was a metric created by IBM to show, how many qubits are actually useful in the machine, and kind of it's meant to create industry standardization. So what it actually says is, what is the largest square circuit that I can run on a quantum machine? So that looks at the number of operations being equal to the number of qubits that are used to run a particular algorithm. So they kind of have a set of algorithms that are used for this. And what we see is Quantinuum have the largest quantum volume at the moment. But what's interesting here is that it's only a 16 by 16 circuit, and that's on a 32 qubit device. So what this really shows is, even though there are companies out there that have 50, 100 plus qubits, it doesn't necessarily mean that they're able to run the biggest and best algorithms. Now, it is important to consider that just because it can't run a square circuit of that size, it will be able to run, say, a circuit with lots of qubits that are involved, but not that many operations, that sort of thing. So this isn't the be-all and end-all, but the idea is that just because a quantum computer is bigger doesn't mean it's better. We need to be considering the properties that were on the last slide. And then the other thing is that quantum algorithm development must be ahead of machine development. So just because we're not able to run algorithms at the moment which surpass classical computers, it's the case that we need to be ahead from an algorithm perspective, because these aren't easy things to create, these aren't easy things to run, and people need to be thinking about what the specific use case is to them, way ahead of the machines actually being available. So there are lots of developments, there are exciting things happening, but we're not quite at the stage where it's surpassing classical machines. Okay, so I'll just give a brief overview of some of the use cases. Now, I've referred a lot to the idea that modeling that quantum is quite similar to what we see in kind of nature, and atoms and molecules exhibit quantum behavior. So it actually means that quantum machines are very good at modeling physical systems, so modeling molecules and interactions and things like that. So from my personal belief, I think this is really one of the first places that we'll start to see an advantage, a useful advantage of quantum machines over classical. Also, where we have combinatorial optimization problems. So a lot of, when we're looking at kind of combinatorial optimization problems, the actual algorithms that would use to solve these are often the same as the ones that would use to model physical systems, because when we're looking at physical systems, we're often looking at an energy minimization. And for the combinatorial optimization problem, we're also looking at finding the optimum solution, which is often like a minimum of something. So when we kind of look at lots of different options together, combinatorial optimization and modeling of physical systems is very similar. And I think this is very important to keep in mind, that the power of quantum computing is really in the way that you adapt your use case for the algorithms that are out there. So, lots of people will talk about use cases, as even I am today, to say, yeah, quantum computing is great at, derivative pricing or modeling molecules, that sort of thing. But actually, people need to be thinking, what type of problems am I looking at that are optimization problems that can be mapped in the same way that these are? Because when we look at quantum computing algorithms out there today, there aren't that many different algorithms out there which are used. We kind of have lots of variations of, groups of algorithms, but the use case, if you think of, a new use case for quantum computing, it's very unlikely that you'd also be creating a new algorithm. You'd just be mapping your use case to an existing algorithm. And then the other thing that we look at is pattern recognition, so grouping, and we're just able to look over lots of different types of combinations, and quantum computing can often find quite interesting patterns that classical computers aren't. Okay, so to go into a little bit more detail here, when we do modeling of molecules at the moment, we're actually not able to model very large chemical systems without making quite severe assumptions. So when I was looking at modeling hydrogen chains, for example, it's the case that if you want to find the ground state energy of a hydrogen chain which has a specific number of hydrogen atoms in it, you'd only be able to get up to kind of 14 or 16 hydrogen atoms kind of in one chain, where you'd be able to completely find a solution using classical methods. And that's just because it's very difficult to model exactly, but we are able to model much larger systems if we're willing to make some assumptions. But with a quantum machine, for example, we can do an encoding where we have one spin orbital maps to one qubit. So therefore, if we had 20 well-connected qubits, then it's the case that we might even be able to see an advantage over classical machines. But obviously, to actually be something that's of use to people in the industry, say like pharmaceuticals or kind of chemistry researchers, we would still need a lot more than 20 to be able to model molecules that they would be interested in. So this is one really exciting area to look out for, and hopefully would be able to see some gain soon. Obviously, I'm not making any promises or predictions. Now, obviously, coming at this from a financial services background, one thing that is quite of interest is fraud and customer experience. So at the moment, a lot of the fraud detection systems out there have an unnecessary rate of false positives. And that's just because there are so many different variables which go into this type of investigation. It's very similar with credit scoring. It can take a very long time to do. And the current systems that we have are very limited in the different factors that they're able to look at. So by being able to expand and look at, say, more factors or more variables, then it's the case that we could do more nuanced credit scoring and potentially really open this up and reduce the number of unnecessary no's that we have while still being risk conscious. And obviously companies are able to determine the amount of risk that they're willing to take. So what this is about is just really understanding more factors when it comes to your customers, and being able to provide the best products for them. So there are also many use cases that are in investment banking that also can be or are also like combinatorial optimization problems. We have a lot of different factors, and this could be a potential interesting area for quantum computing. So specifically looking at things like liquidity management, derivative pricing, so like Black-Scholes, as well as risk analysis. And when we look at quantum computers, when we say, are quantum computers able to perform something better than a classical machine, we're actually looking at a few different factors. We're looking at the number of variables. We're looking at, well, can a quantum computer perform this faster than a classical machine? Are they able to perform it more accurately? Are we just looking at larger scenarios? Depending on your use case or depending what you're interested in is going to depend whether you're interested in speed, accuracy, or size. But specifically for these use cases, we're expecting that it could potentially be faster, but also a larger size. So we're able to just also manage the complex regulatory requirements that we have as constraints of our quantum algorithm. So as you can see here, there are lots and lots of different use cases that we have. And it's exciting to think about how these could be used within the chemistry as well as financial industries. But there are many, many more industries which are likely to be impacted by quantum computing. So it's quite exciting to see what's going on in the future. With quantum computing, it's the case that you can already have a go now at developing your own quantum algorithms and actually using real quantum computers. There's lots of different sites that are open to that right now. Some of the popular ones are Amazon Braket, as well as IBM Qiskit. So it's very exciting, and I'd advise you all to have a go if you have the time. And now I'll open this out to questions.
Thank you very much, Jen. This was a very interesting topic, and I think a lot of us learned a lot. So we have a few questions in the chat, actually. One from David. From what we know today, what is the most likely practical application of this technology in your view?
That's a good question, because even though I was referring to quantum chemistry potentially being one of the first areas, it's probably very unlikely that that's going to be practical for a lot of people, or it's going to be something that's really used. So one I didn't talk about that I find quite interesting is the idea of route optimization. And the reason that I think that could impact more people is the fact, we've got like delivery companies, or basically all companies have some kind of supply chain. And the idea of optimizing those is probably one of the most exciting and interesting practical applications that is likely to affect a larger audience.
That's great. Thanks a lot. Another question from the chat is, when are the likes of Google and IBM predicting commercial scale usage of quantum computer to be the norm?
I think it's the case that we're a very, very long way off that. And even though there are lots of interesting use cases, I don't think quantum computing will ever be the norm. There's always going to be large barriers to using quantum computing. I mean, the first one's obviously going to be the people that are able to use it, the size of, if you want to use large quantum computers, I imagine that could be quite expensive. These companies have put a lot of money into research and development to actually use a quantum computer that has an advantage over a classical one. I mean, I don't have any knowledge of what will happen. No one does, but I think that's going to make it quite prohibitive. And just the fact quantum computing is not good at solving every problem. It has a very, very limited number of things that it's able to do well. So if that's relevant to kind of your use case, then great, but it's probably not. And quantum computers will also be a very, very small part of any kind of use case or algorithm. Most of the majority of what you do on a quantum computer, you kind of do a large amount of like classical like Python code, and then you just like send a little bit off for processing to a quantum computer and then just have it back. So I think I've diverted a bit away from your question, but I don't see it happening anytime soon. And I don't see wide scale usage of quantum ever. But I think it definitely has some interesting use cases in small areas.
I agree, thank you. So you've just touched on relevance. So I guess my next question is, what is the relevance of quantum to other technology areas such as AI, data, and cloud, for example?
So there's obviously lots of stories in the news about, ChatGPT, generative AI, and because that's, quite a cutting edge technology, and because quantum computer is also, a very advanced technology, people are often thinking, well, how do they work together? And quantum computers actually don't work that well with big data. And that's because the encoding from the data that you have into the quantum computer is very difficult to do. But when it comes to cloud, as we've seen, a lot of the more advanced quantum computers are absolutely huge. So it's something that you're probably not going to have on site. So it's likely to be a service that you access via the cloud. And there are already services which are provided by AWS, Azure, and IBM Cloud. I believe there are some others too, where you can actually really easily integrate quantum with your existing cloud infrastructure.
That's great, thank you. And I think we have time for one last question. If I wanted to learn more about quantum, how would I do it? Yes.
Yeah, that's a great question. So there are many tools out there which can be used to create your own quantum algorithms. And I would definitely advise people to actually, we have like Qiskit, Penny Lane, and there's some others, but those I think are two of the easiest to learn, Braket as well. If you look up existing quantum languages and frameworks, then actually trying to get some hands-on experience of using a quantum computer is probably going to be your best way of actually understanding how it works, because you can go to lots of presentations, you can read lots of things, but until you actually get hands-on with things, it's hard to understand how these strange ideas are able to be used every day.
Great. Thank you very much. This was very, very interesting, and I definitely learned a lot. Thank you very much to everybody that's joined us. And we'll send a copy of the video that has been recorded to everybody. If you guys want to watch it sometime later. Jen, anything else you'd like to end us with?
This is my contact information. If anyone has any follow-up questions after this call, then please feel free to reach out.